Today I start one important topics which is related to normed linear space. We start from basic definitions. We first talk about continuous functions and obviously we show about continuous and uniformly continuous functions. Let x dx first we talk about in metric space, then we also going to norm space. Okay, then x dx and y dy be a metric space and c be a non-empty set in x. Okay, then what happened? Then and let if c to y be a mapping, and let if c to y be a mapping. Okay, if c to y be a mapping, then first f is said to be bounded. F is said to be bounded if fb is bounded. If fb is bounded for every bounded set in C. For every bounded set V in C. Now we talk about f is continuous at point x belongs to C. At point x belongs to C if for each epsilon greater than 0, if for each epsilon greater than 0 there exists delta equal to delta epsilon x greater than 0 such that dx dy fx fy less than epsilon whenever x belongs to C with d of x xy less than delta. Okay, next we talk about uniformly continuous. F is uniformly continuous at point x belongs to C. No, sorry, uniformly continuous means not a point. Okay, we write here wrong. Uniformly continuous on C. That means in whole domain. Okay, in whole domain this one is uniformly continuous if for each epsilon greater than 0, there exists delta depend on just epsilon greater than 0 such that here dy fx fy less than epsilon whenever x belongs to C with d of x xy less than delta. Okay, not a problem at all. So we talk about those portions in matrix space. Okay, now we're going to norm space. How this one is formed in norm space? We're not in its total portion, we just erase this necessary portions. Okay, where some change occur, we erase that portions and continue next one and remain same. Okay. Okay, now we're going to discussion about that. Here x norm x, y norm y, be norm spaces. Okay, and C be a non-empty set, and let f C to Y be a mapping. Then f is said to be bounded if f be bounded for every bounded set B in C, and f is continuous at point x belongs to C if for is epsilon greater than 0 there exists delta epsilon x greater than 0 such that norm of fx difference fy here with norm y with respect to y less than epsilon whenever x belongs to C with x difference y norm a with respect to norm x less than delta. And here f is uniformly continuous on C if for each epsilon greater than 0 there exists here f of x f of y less than epsilon and with x difference y with respect to x less than delta. Okay, here xy is arbitrary, and here one thing is not written here. F is continuous on C means f is continuous at every point of C. Okay, so we understand this basic definition of bounded function and continuous function and uniformly continuous functions on metric space and norm space. Norm space, how this functions is defined, we also discuss now. Okay, so we are also understand these portions. Now we're going to further discussion of some proposition. We erase that portion and going to discussion of some proposition. Okay, so we write this proposition here. Let xd and y row be matrix spaces. Let C be a non-empty set. Let C be a non-empty set of X. And let if C to Y be a Lipschitz mapping. Then f is uniformly continuous. Okay, so we prove now. Let xd and y row be matrix spaces. Let C be a non-empty subset of X, and let fc to y be a Lipschitz mapping. Then we have to prove that f is uniformly continuous. So how we prove this? This one is too easy, but we prove it for better. So let epsilon greater than 0 be given. Okay, then we're going to definition of Lipschitz without generality, without loss of generality, L greater than 0 some number, and set epsilon equal to delta equal to epsilon by L. Okay, then what happened? Then for xy belongs to C with dxy less than delta, we have what? we have rho of fx fy, okay, less than equal to L of txy. This one happened because this function will if satisfies the Lipschitz condition. Okay, so in metric form this one happened. Okay, in norm also this one is too easy. Norm of fx minus fy equal to L multiplied by norm of x minus y, and here in modulus from mod of fx minus fy less than equal to L mod of x minus y. Okay, but we write it in this way, and obviously this one L delta less than, and L delta equal to what? L epsilon by L equal to epsilon. So what we get? We get this one, rho of fx fy less than epsilon for d of xy less than delta. Okay, so what we get? We get f is uniformly continuous, not a problem at all. Okay, so we easily prove that f is uniformly continuous. So now we erase that portion and going to, obviously this one is norm. How have happened we also talk now here. Okay, we erase this portion, this one is needed portion, then also going to, okay, discussion about that. That means what we do here, norm x and here norm y, x norm x and y norm y be normed spaces. Okay, and let's see be a non-empty subset of x and x. Okay, because fc to y here, and let fc to y be a Lipschitz mapping, then f is uniformly continuous. Then what happened? Let epsilon greater than 0 without loss of generality, L greater than 0, delta equal to epsilon by L, choose or set. Then for xy belongs to C with txy, here some change is needed. Okay, here what happened? Here so simply we write it now, this one with respect to x. Okay, and here also some change occur. Here obviously norm of fx difference fy with respect to y, and here obviously we write this one, norm of x difference y with respect to x, and this one is not a problem, then all are same. We just write conclusion part here, norm of fxy fy y less than norm of x difference y with respect to x less than delta. Okay, I think this one is okay. Then we prove it in norm space. Now we're going to discussion about jointly continuous. Obviously norm is continuous and some addition functions jointly continuous and scalar multiplication is continuous. We're going to discussion about another propositions related to norm is continuous and some addition function is jointly continuous. So we talk about this portion now. We also going to discuss about this portion. Now we write this proposition first. Okay, statement of this proposition, let x norm be a normed space, with over k. Okay, sorry, here we erase that portion, over k, some field k, and for xy belongs to x and alpha belongs to k and alpha belongs to k, define f of x plus xy equal to x plus y, g of alpha x equal to alpha x. Okay, we have the following. Then we have the following. First one, the norm be continuous. The norm be continuous first. Second one, The addition function f is jointly continuous. The addition function a being jointly continuous on x Cartesian product x, and c the scalar multiplication function g is continuous. The scalar multiplication function g is continuous. Okay, so we also discuss proof of that portion. Okay, so easily we write it now. Now we're going to prove about that. So prove also easily we write it. First marked as a, and let x belongs to this x, and let x and be a sequence, x and be a sequence in x such that xn tends to x. Okay, then what happened? We mod of this one, difference this one, obviously less than equal to norm of x and difference x. Okay, we also, that means we also proved this inequality in previous day or previous class. Now we write this one. Okay, just this one is familiar, some mod of a difference b less than equal to, that means mod of norm a difference norm b less than equal to this one. How this one is that means done? If we talk about now, then this one is better. This one is happened in this way. Here norm of a equal to what? Norm of a plus b difference b equal to what? Norm of a difference b plus b equal to what? Less than equal to norm of a difference b plus norm of b. Okay, not a problem at all. Then what happened? Then this one, norm a difference norm b less than equal to norm of a difference b. And similar, if we interchange a b, then norm b difference norm a equal to norm of b difference a, and norm of b difference a equal to norm of a difference b. So this one mod less than equal to this one, not a problem at all. Okay, so we erase that portion now. Now we're going to prove of that. So xn tending to x means this tends to 0 as n tending to infinity. And otherwise, if we talk more, then if there exists some k belongs to natural number n greater than equal to k, norm of xn difference x less than epsilon for all n greater than equal to k. Okay, we not write more, we just write this one is too easily. Okay, this one tends to 0 as n tends to infinity. Therefore, simply what happened? Norm of xn difference norm of x modulus tends to 0 at n tending to infinity. So what we get? We get this. Therefore, norm is continuous. Okay, norm is continuous. Then obviously we just, that means since x is arbitrary, norm is continuous at x and x is arbitrary, so norm is continuous on this capital X. Okay, then not a problem at all. We're going to next portion. Okay, we easily, this one is done. Not write more. If we want to write more, then obviously this one happen. That means there exists natural number k. Then this one is also talk this one, not right here now. I erase that portion and going to further discussion of another two portion. This one is too easy portion, but we have to know about that. That means we have to gather knowledge about that. Okay, so b, that means this sum function is jointly continuous. Now write xy belongs to x cross x. Okay, let x and y n belongs to be a sequence in x cross x such that xn tending to x and yn tending to y. Okay, then note that this equal to what? This equal to xn plus yn difference x plus y. Tends to 0 since x tends to x and y tends to y. This means h n tends to infinity. Okay, then this one is too easily done. That means f is continuous at xy. Hence what happened when f of x and y and difference f of xy, norm of this tends to 0 as n tending to infinity. This implies that f of x and y n tends to f of xy. Okay, so this implies hence f is continuous at xy. Okay, so since xy is arbitrary, therefore we conclude that f is continuous on x cross x. So therefore we conclude that f is continuous on x cross x. Okay, now we're going to discussion about third portion. We erase that and going to third portion. That means f is jointly continuous, we also prove. Okay, that means the sum function or addition function is jointly continuous, we also prove. Now we're going to scalar multiplication function g is continuous. Okay, so we marked as 3. Let alpha x belongs to k cross x. Let alpha n x n be a sequence such that alpha n tends to alpha and x n tends to x. Then g of alpha n x n difference g of alpha x equal to norm of alpha n x n difference alpha x. Okay, this equal to norm of alpha n x n difference norm of alpha n x plus alpha n x difference alpha x. Okay, then this one equal to norm of alpha n different x n difference x plus x alpha n difference alpha. This less than equal to mod of alpha n norm of x n difference x plus alpha n difference alpha mod of this norm x. Okay, this marked as 1. Now alpha tends to alpha n tends to alpha, that means what? Alpha n tends to alpha, then what happened? Since this one, then there exists m greater than 0 such that norm of alpha n less than equal to m for all n belongs to natural number. Okay. Sorry, this one is not happened. If alpha tends to this one, that means alpha is bounded, alpha is convergent, alpha n be convergent sequence. So this implies alpha n be bounded, because every convergent sequence is bounded sequence. Okay, so this one happened this. Okay, not a problem at all. Then we going to next. Then we also talk about that since alpha tends to alpha, then this implies norm mod of alpha n difference alpha tends to 0. Okay, and here not needed norm this one, because alpha belongs to a element of k and alpha n belong a element of k, so just mod of alpha is necessary, not needed. This one is norm. If you that means write norm, then not a problem at all. But someone also think about that you not known this one, but mathematically this one is not wrong. Okay, so we write this one, alpha n tends to alpha, so mod of alpha n difference alpha tends to 0, and obviously we also known about that xn tends to x. This implies that norm of xn difference x tends to 0. Okay, as n tending to infinity, and here also as n tending to infinity. So what we say from 1 we erase that portions, and just this one is right here, and remaining portion we erase. Then what happens? This one less than equal to m norm of x and difference x plus here this one is alpha and difference alpha norm of x. Okay, so what happened? This tends to 0 as n tends to infinity. Okay, so what we get this one, we get norm of c of alpha n x n difference c of alpha x tends to 0 as n tending to infinity, tends to 0 as n tending to infinity. Okay, then g is continuous on k Cartesian product x. So we write here, therefore g is continuous on k cross x. Okay, therefore g is continuous on k cross x. So we discuss this portion. Norm is continuous, addition function f is jointly continuous, and the scalar multiplication function g is continuous, and obviously continuous and uniformly continuous, and Lipschitz function implies uniformly continuous function in norm space and matrix space. We will also discuss these problems today. Okay, I think all are understand those problems. If any problem occur, then obviously if you raise any question in your comment box, and if you like and also get this type of videos, then subscribe this channel. And if you like those types of video, then if you obviously, that means it gives like in this video. Okay, so I'll stop here.